In standard quantum mechanics, the energy of a photon is defined by this equation. Energy equals Planck's constant multiplied by the speed of light divided by the wavelength. Within this model, Planck's constant, the variable h, is treated as an axiom. It is a fixed value used to calculate quantum behavior, but the theory does not describe a specific mechanical mechanism that generates the constant itself. This raises a question of origin. Is h an arbitrary rule of the universe, or is it a value derived from physical geometry? Identifying a mechanical origin for Planck's constant would link abstract quantum rules with the physical principles of classical continuum mechanics. In 2026, Menelaus Georgiades proposed a framework called the elastic continuum model to address this question. This model posits that vacuum space acts as a continuous elastic medium, or a plenum. Here, energy quantization results directly from the medium's geometric properties. This led to a specific conclusion. Every photon in the universe possesses the exact same transverse amplitude, regardless of its energy or wavelength. This contrasts with common mechanical intuition, where we might expect higher energy waves to create a larger spatial disturbance, or a taller wave. We have to look at how classical elastic strain math applies to a vacuum to see why it requires a universal, constant amplitude. The first step is defining the structure of a single photon within the elastic plenum. The model describes the photon not as a point particle, but as a localized transverse wave packet propagating through the medium. This formulation describes the wave packet's physical deformation. The first term represents the Gaussian envelope, defining the wave's boundaries based on its spatial localization radius, sigma. The second term is the internal oscillation, where wave density is determined by the wave number, k. The variable a represents the fundamental oscillation amplitude, or the physical height of the wave. This mathematical packet represents a photon moving at speed c. From this geometry, we can calculate its energy. To calculate the energy trapped within this photon, we apply classical mechanics. Elastic energy is found by integrating the squared elastic strain across the wave, multiplied by the stiffness of the medium k. The calculation relies on this integral of the squared spatial derivative, partial u over partial x. This derivative represents the deformation gradient. When we differentiate the wave packet equation, we find that the strain is heavily dependent on the wave number, k. In wave mechanics, the wave number is inversely proportional to the wavelength. We can visualize this through the slope of the wave. For a long wavelength, the tangent lines along the curve are shallow and gentle. But if we look at a short wavelength with the same height, the tangent lines become much steeper. Steeper slopes represent a higher deformation gradient, which then exerts a more severe elastic strain on the vacuum medium. Integrating this strain across the entire packet results in this energy relationship. The energy scales directly with the medium's stiffness and the square of the amplitude, and it scales inversely with the wavelength. Under these classical rules, photon energy is a product of physical steepness and spatial strain. We can now compare the classical elastic model with the standard quantum definition. On the left is the axiomatic quantum energy of a photon. On the right is the derived elastic energy from the continuum model. Equating the two reveals the underlying relationship between these variables. In this equivalence, wavelength appears in the denominator on both sides. This allows the wavelength to cancel out of the equation entirely. By rearranging the remaining terms, we can isolate Planck's constant. This shows that the value of h is independent of the photon's wavelength. Planck's constant is instead defined by the stiffness of the vacuum, the speed of light, and the physical amplitude of the wave. This relationship has a significant implication for the geometry of the vacuum. The stiffness of the plenum and the speed of light are invariant properties of space. Because h is a universal constant, and k and c are also constants, the math requires the amplitude a to be constant for all photons. Using the known values for Planck's constant and the speed of light within this elastic framework, we can calculate this universal amplitude. It is approximately 3.96 times 10 to the negative 16th meters. Planck's constant is the direct mathematical consequence of this constant geometry of elastic shear. We can apply this result to compare different types of light, like visible light and X-rays. Earlier we noted the bias that a high-energy X-ray should be taller than a low-energy visible light wave.
The model shows they actually share the same height. Both are bounded by the same universal amplitude limit. An X-ray's energy comes from its spatial gradient. To fit within a much shorter wavelength, the wave must have a much steeper internal slope. This steepness creates a high shear strain on the vacuum continuum, resulting in higher energy. Continuum mechanics and quantum mechanics align at the geometry of the wave. The energy of a photon is a function of geometric slope, not height.